Most of the time, we treat numbers as rigid blocks of data. They are absolute tools built for a specific job: counting, measuring, tracking. We rely on them because they behave like an inflexible structure, seemingly devoid of elasticity. But recently, a math enthusiast hit a specific milestone, turning exactly 28,113 days old. Instead of just logging that number as a date, they decided to run a peculiar mathematical experiment on their own age. They stopped treating 28,113 as a fixed, unyielding measurement of time and started looking at it as pliable raw material. When ordinary integers are detached from their real-world meanings and treated as flexible codes, they start to reveal entirely hidden properties. Take a look at this abstract machine. We are going to program it with a single rule. Take a number and replace every non-zero digit with its corresponding prime number, a number divisible only by 1 and itself. If it finds a 0, it swaps it for a 1. When we feed the age 28,113 into the system, the 2 becomes a 3, the 8 becomes 19, the 1s become 2s, and the 3 becomes a 5. Run those newly swapped digits together, and the original age expand into 319,225. Break that down, and you get exactly 565 squared. This behavior is a documented phenomenon logged as sequence A048383 in the OEIS, the Online Encyclopedia of Integer Sequences. This database categorizes numbers that yield a perfect square when manipulated with this exact prime number swap. This raises a question: is 28,113 an isolated mathematical fluke, or is it one coordinate in a massive, unexplored set of manipulatable numbers? To find out, we have to widen the net. We can instruct a computer to scan every single integer from 0 all the way up to 40,000, passing each one through our prime replacement rule. The algorithm is strict. It will discard any result that is messy or irregular, exclusively keeping the numbers that compile into a perfect square. Watch what happens as this massive grid of 40,000 data points filters down. The property turns out to be rare. The vast majority of numbers fail the test, leaving only a scattered handful of survivors behind, like 13, 113, and 2,410. When applying a rigid algorithm to raw data, perfection is exceedingly scarce. But we can change the target. Let's adjust the algorithm so that instead of hunting for perfect squares, it only accepts numbers that, when swapped, result in a prime number. We run the same scan from 0 to 40,000 using this new parameter. Look at this chaotic cloud of 5,629 prime results. To find structure, we introduce artificial constraints. Requiring pairs of consecutive integers drops the noise to 580. Tightening to triplets leaves 103. Searching for a continuous run of 5 leaves only one run, starting with 7,116. Order often emerges only after we actively constrain the chaos, forcing the data to reveal a specific truth. The best part of this process is that the initial rule we used can be scrapped and rewritten from scratch. Rewiring our machine's core function, we replace each digit with its square to find non-palindromic numbers that transform into perfect palindromes. Take 28,028. Moving through the algorithm, the 2s become 4s, the 8s become 64s, and 0 stays 0. The output, 4,640,464, perfectly mirrors itself. Adjusting one line of the operational code shifts the focus of the search. Testing this new rule up to 40,000 uncovers 96 non-palindromic numbers that transform into perfect symmetry. Moving through this endless, expanding geometry, you begin to realize something profound about the true, hidden nature of recreational mathematics. Our base 10 number system provides an infinitely pliable sandbox. The digits we normally use to measure distance or calculate taxes can be pulled apart and recoded into entirely new sequences. Thousands of sequences logged in the OEIS were found by people armed with simple rules and a sense of curiosity. Mathematical discovery can stem from a simple creative constraint, a willingness to iterate, and the imagination to ask, what if, about something as mundane as your age in days.